Hello everyone, my name is Xiaohui and I am a master's degree candidate at Shandong University in China. My topic today is LaserAdv, laser adversarial text on speech recognition systems. Many researchers have increasingly focused on attacking ASR systems using audio adversarial examples, but they are almost still within the audible frequency range. Light commands is a type of audio injection attack which employs the photoelectric and photoacoustic effects of MEMS microphone, converts light to sound and inject malicious audio signals into microphones. Its attack scenario is the victim is not interacting the ASR. Inspired by light commands, we proposed LaserAdv, a method that leverages laser beams to inject adversarial perturbations into voice control systems. Compared to light commands, LaserAdv effectively reduces the SNR required for successful attacks. This reduction in SNR has several notable benefits. 1. Broader range of vulnerable devices. 2. Improved power efficiency and attack stealth. 3. Longer attack range. To investigate the feasibility of laser perturbations, we conducted experiments to analyze the system responses of microphones to laser beams. The left figure shows the frequency response codes of 3 devices, the laser diode, driver board, and the MEMS microphone. We can see the frequency response of the microphone shows a pronounced drop with increasing frequency. It's a frequency selective fading, short for FSF channel for laser signals, resulting in significant signal distortion. Then we use 5 devices to record audible and laser perturbations respectively. Each of the images of laser perturbations exhibits 2 or 3 types of distortions. 1. Additional noise. 2. Weak response, resulting in a low SNR. And 3. Distortion caused by FSF. I will introduce corresponding methods to address the distinct distortion. This is the threat model of LaserAdv. We assume the victim is speaking any voice commands at the time of the attack. The adversary must simultaneously fulfill the following conditions. Synchronization-free. It describes a scenario where perturbations, although delayed by up to half of 1 second, can still affect that part of voice commands. Transferability. It refers to the perturbations generated for the white box ASR system, deep speech, which can be utilized to attack black box systems, such as iFlyTech and Whisper. Universal. It refers to the ability of a perturbation to effectively attack over 10,000 users' voice commands. Finally, inaudible and targeted. Now I will introduce the design of LaserAdv in detail. Our objective is to generate an integrated adversarial perturbation, short for IAP. Firstly, unlike previous methods, the adversarial perturbation delta is not subject to strict constraints. Secondly, transferability arises from the observation that different ASR models, despite their unique structures and parameters, often capture similar high-level features for targeted voice commands. This consistency not only leads to identical results for similar speech inputs, but also creates uniform vulnerabilities across models. Therefore, we consider building a dataset containing a wide range of elements of speech, including different volumes, accents, speech rates, background noise, and more. After training, we can achieve a perturbation potentially effective for attacking models with different architectural parameters. The next is to accomplish time and content independence. We randomly choose a time delay uniformly within the range from 0 to the difference of x and delta to compute the gradient at each iteration, and the delay can be set to greater than 20 sample points to make the perturbation universal. The optimization problem should consider the generalization of the perturbation across a wide range of audio inputs, and by normalizing and adjusting the volume, enhancing the efficiency and helping prevent non-convergence issues. To address the issue of reduced intensity due to the limited gain of microphones, we impose certain constraints on the amplitude of the perturbation according to the frequency response of device to set parameter B. Successful attacks can be achieved even when the device receives only small amplitude perturbations. By setting a lower bound A on the perturbation, we avoid overly stringent constraints that could hinder the generation process. FSF causes the high-frequency components experience much greater attenuation than the low-frequency components. Therefore, we propose a SAE-TFI method to compensate for the attenuation of high-frequency components. We apply short-time Fourier transform to the generated perturbation delta to convert it to the frequency domain, obtain the amplitude spectrum and phase spectrum, perform linear enhancement on the amplitude. If the frequency is greater than the cutoff frequency, multiply with the enhancement ratio coefficient. Finally, use the inverse STFT to obtain the enhanced perturbation. Then we can create adversarial perturbations taking into account all the factors involved. Now I will move to the evaluation of our approach. We target 3 ASR models and 6 smartphones. The dataset contains more than 10,000 voice commands totally. We utilize a 5 millivolts red laser diode directing the beam vertically towards the smartphone, and we position a loudspeaker adjacent to the microphone to play voice commands. We use a tag success rate to quantify the performance of LaserAdv. First of all, LaserAdv has the ability of a perturbation to effectively interfere with over 10,000 users' voice commands. Our results show that the success rate remains consistently high under both delay conditions for 3 ASR models. Specifically, the success rate of attacking deep speech without delay reaches for 100%. In the physical scenario, when there is no delay, the average success rate of deep speech, whisper, and eye-flat tag are 100%, 92%, and 88% respectively. When the delay was set to half of 1 second, eye-flat tag was the most resistant. The success rate dropped to 75%. Now I will show some impact factors on LaserAdv. The first one is the impact of varying laser power levels. We employ a laser power meter to measure the maximum power of laser diode at 6 millivolts. When the power is 2.5 millivolts, the attack becomes effective, but the success rate is only 10%. As the power gradually increases, so does the success rate. Upon reaching the rated power of the laser diode at 5 millivolts, 100% success rate can be achieved. We further investigate the attack performance changes due to different loudness of the perturbations in LaserAdv or malicious voice commands in light commands. The user speech was delivered within the range of 70 to 80 decibels. At an intensity ratio of 20%, LaserAdv can attack successfully. When the laser intensity matches the user's speech intensity, LaserAdv achieves a success rate of 80%, while light commands is just successful under this condition. With increasing intensity, the success rate can be up to 100%. Our experiments confirm that LaserAdv requires substantially lower perturbation intensity compared to light commands. The third one is the impact of attack distance. The left figure shows that as the distance increases, the success rate on smartphone decreases. At 4 meters, the success rate is about 60%. Then we conducted a long-range attack in a wide corridor, where the laser diode was significantly far from the MEMS microphone. Light commands achieves a 50% success rate at 20 meters, dropping to just 5% at 80 meters, and becoming ineffective beyond that range. In contrast, LaserAdv boasts a remarkable performance with a success rate exceeding 95% within 60 meters, 80% at 80 meters, and the ability to extend up to 120 meters. Then we employed 6 smartphones for experiments. It is evident that the attack on Honor and Samsung yields the most favorable results, with a remarkable 100% attack success rate. The performance on other 4 smartphones is comparatively lower, though still significant, with a success rate exceeding 72%. In summary, we introduced LaserAdv, a new method for launching adversarial attacks on ASR systems via laser perturbations. To solve the problem of distortion within laser channels, we have proposed a SAE-TFI method and further optimized the IAP generation objective function to facilitate more practical attack scenarios. We have conducted plenty of experiments to prove the efficiency of LaserAdv. Our evaluation results show that LaserAdv can launch attacks on 3 ASR systems, and the maximum attack distance can be up to 120 meters. And that's all. Thank you. Any questions?